we will have KAC theta B m, and m we know is nothing but under root HP divided by KAC, right? So Q fin. If we use that in that expression, we will have under root HPKAC times theta B. So this is the heat transfer from the fin, which is of infinite length. This expression is very important for calculating the heat transfer from the fin. Alright. So M is the term which is related to the thermal conductivity. If we have all of the things constant, H we cannot touch. If we have particular geometry fins of P and AC, also we cannot touch. So the only thing which is concerning is the thermal conductivity. So if we have fin of low thermal conductivity, then M value will be higher, right? So for a given location, it will have less temperature as compared to the fin having high thermal conductivity. So what I mean by this, let me plot in some graphs so that you can understand in a better way. So T minus T infinity divided by TB, T naught OTB. If we plot along the length, so let's say this is the length, total length, this is x equal to 0. If I'm plotting for different fin lengths, x equal to 0, this variable value will be 1, right? From this x equal to 0, this theta by theta b will be at x equal to 0. So that is theta by theta b only, which is we are plotting. So for different values of m, we can plot like this. Alright. So if we cut at any location x, m, let's say m1, m2, m3. So m is related to the thermal conductivity, right? From this, if all other things are constant for a given material fin and for a given environment condition, for a given fin geometry, right? So for given fin geometry and for given environmental conditions, so m will be dependent on thermal conductivity. If thermal conductivity of the fin is low, m will be higher. If m will be higher, it means it will make this term as low, which means theta by theta b term will be low, right? For low thermal conductivity value fin. Okay, it means fin will be closer to the environment temperature. Environment temperature, and it means that fin is not enhancing the heat transfer that much. Okay, this can apply like that. Okay, so next case we can see that has finite length fin. To finite length fin also, we can have two cases. The case in which we are not considering the tip heat transfer, and the case in which we are considering the convection from the tip. All right, so we will consider the case with insulated tip, means we are not considering the heat transfer from the tip. All right, so in that case 2a, we can write like that: case 2a, finite length fin with insulated tip. In essence, it is not insulated, and we are just not considering the heat transfer from the tip. Or adiabatic tip, right? In that case, because it is finite length fin, so the tip temperature will not be the ambient temperature. Mind that. Okay, so tip can convey the heat transfer to the fluid, have the capability to convey the heat transfer to the fluid, but we are not considering that. Okay, so these situations can be possible when we have very thin tip, right? So that we can assume the, let's say this is base, assume the tip to be insulated. So this is the ambient temperature, let's say, and it is having some that with temperature variation, and this slope we are assuming that this slope d theta by dx is 0, means no heat transfer from this side, right? From this step, heat transfer rate from the tip is minus Ka C dt or d theta by dx is 0. Right, slope is 0. All right, so this temperature will be having some TL, and this excess temperature on the base side the same as TB, theta B, sorry. So the fin, in a sense, can participate in heat transfer from the both lateral sides as well from the tip. Lateral side, what I mean, like the parameter of this, and from the tip also, right? So in this case, for this particular case, we are assuming that tip heat transfer is very less than the Q lateral. It means Q tip is neglected, right? So total heat transfer from the fin is only because of lateral sides. Okay, so again we should start with that solution. So we will follow texts. Okay, I am following from the Syngel heat transfer book, and in that it is convenient to use this form of the solution, this form of the Finn heat conduction analysis that we did in the starting of this, as A cos hyperbolic mx plus b times, mind that h is not heat transfer coefficient, it is cos hyperbolic, cos, we pronounce it right, cos, and sine mx, sine hyperbolic. All right, so a and b we have to find by applying the boundary conditions. So the first boundary condition, we have it at x equal to 0, theta is equal to 0, theta b, and x equal to L, the tip, the slope of the temperature profile or convection to the ambient is 0. All right, so from the tip, heat that is conducting to the tip is not going out. All right, so if we use these two boundary conditions, we can find a and b values. All right, so first we will use the first boundary condition. Theta will be theta b at x equal to 0. A times cos hmx will be 1. Cos 0 is, cos hyperbolic is also, cos hyperbolic 0 is also 1, plus b sine hyperbolic 0, it is 0. So a will be theta b. The next, we have to differentiate this to find the d theta by dx value of this expression. Right, so when we differentiate it, we will have m times a sine hyperbolic mx plus b cos hyperbolic mx. You can refer the mathematics books, the derivative of sine and cos hyperbolics, right? A is theta b, so it will be 0, this left hand side on the at x equal to L, so this value should be 0 and x equal to L. So put that 0 equal to m times a is theta b sine hyperbolic mx L, b we are finding cos hyperbolic ml, so b we can find as minus theta b tan hyperbolic ml. And one more thing, we need to find d theta by dx at x equal to 0 to find the heat transfer, right? So that will be bm